So now we'll do some applications of Ito's lemma. And so we'll just start off with a little reminder of what Ito's lemma is. And Ito's lemma basically said this: if we had a process that had two components to it. We had a process, and we're going to use the letter S because in the financial world it usually applies to a stock process. But if we have a process, so a process was something that evolves over time. If we had a process that could be depicted as having two components to it, one component, a normal mathematical component, which basically will typically represent a rate of growth due to interest. So maybe a percentage, we use the Greek letter mu to mean a percentage in change, times the price of the stock. It doesn't have to be times the price of the stock, just any function here, which is going to typically be an increase in value over time, keeping up with interest. And then another component to it, a stochastic component. This is a component that just has some kind of randomness to it, the thing we can't control. So this ends up being a Wiener process times some function in front of it. We could put many things here if we want. So this could be kind of like an amplitude, something we're multiplying this Wiener process by. Now just a reminder, a Wiener process is a process that evolves over time, starts at a value of 0, and instantaneously at each point in time after it, we add to the current value a randomly distributed variable. So the expected value of this component is to stay at 0. It may go up, it may go down, but the expected value is to stay at 0. So this component is a martingale process. That's a process that at any point in time, if whatever its score is, if you said at some later point in the future, what do you expect it to be? It'd be whatever the current score is. We wouldn't expect it to go up or down. So this part just provides randomness. This part provides an incline that is proportional to how much of a return we expect from this process. So there's a non-stochastic component and a stochastic component. So Ito's lemma comes along and says if you make up any function at all, let's say g, a function g, which takes as input s and t, t being time, any function you can come up with, you can just make up anything. It doesn't have to make sense or anything. You just come up with any function. And as a result of Ito's lemma is that the equation for your new process that you made up follows, this is the non-stochastic component, and this part is the stochastic component, with the same Wiener process that we used for the original. So it just ends up being a different amplitude that we're multiplying the Wiener process by, and possibly a very different non-stochastic component. And the way we calculate these is we take derivatives and, partial derivatives. We take the partial derivative of the new function that you've made up with respect to s. Then we add and multiply that by mu times st. Add the partial derivative of your new function with respect to t plus 1/2 sigma squared, the sigma which came from up here, and the s squared, the s that's the variable s that we're using, times the second derivative of your function with respect to s. Add that all together, and that's the coefficient in front of the non-stochastic part. And then this is the stochastic part. This ends up being sigma times t times this derivative of your function with respect to s. So that's what Ito's lemma says. You could dream up any function g, and then as long as g is based on s, which is an Ito process, and some variable t, which usually maps to time because it's a process. So that'll be a true statement for any function you can dream up. So let's use, just for the sake of doing one, let's look at the function. I'm going to make up a function here called, I'm going to triple the price of the stock. So I'm now coming up with a derivative, right? I'm saying I have a derivative product, G, which will equal 3 times a stock. So let's say, for example, the stock was IBM. And IBM is currently selling for $100 a share. And you come up with some derivative product, which basically somebody would buy, and you will give them 3 times whatever IBM is currently selling for. So how much would they pay for that today? So first of all, by definition, it's a derivative because it derives its value from some equity. So all it is take IBM stock, multiply it by 3, and you'll know what the value of this derivative is. So we'll call it the 3 times IBM derivative. So suppose some company offered this. What would it currently sell for? If IBM is currently selling for 100, what would this derivative sell for? 300, right? Okay. So if we decided to just come up with some new derivative product, and the idea of using Ito's lemma is basically if you start dreaming up derivative products, like maybe you'll dream up a product like, I'll take whatever the price of Microsoft is plus whatever the price IBM is, I'm selling shares of that thing. Like you just start making up derivatives, right? You just package anything together. And you want to know what is the thing worth. So you're coming up, that's your G. You can put together whatever you want. And we originally said that these processes could actually be a vector of processes when we originally defined it. So it doesn't have to be one stock, it could be a collection of stocks. But for this example, we'll have it be one stock. So at this point, we say, okay, my new function is G equals 3 times S. Whatever S is, I'm just going to multiply it by 3. So according to Ito's lemma, we want to calculate the derivative of G with respect to S. That would be the derivative of 3S, which is 3. The derivative of 3S with respect to time, it actually doesn't have any time. This should say 3 times, sorry. So the derivative of G with respect to time would be 0. And then the second derivative of G, basically the derivative of this part, so the second derivative of G with respect to S would be the derivative of 3 with respect to S, which is 0. Okay, so we have the first derivative is 3 with respect to the stock. The second derivative, the first derivative of G with respect to time is 0 because there's no T in this formula. So that's just 0. This is a constant from T's point of view. And then the second derivative of G with respect to S is the derivative of the derivative. So the derivative of 3 with respect to S is 0. So now we take these and plug them into Ito's formula. And I think I got the colors lined up. So this goes here. This one should be red. Sorry about that. That came down red here. And this purple times 0 zeroed out this term. So what we ended up with is 3 times mu st. That's 3 times mu st times dt. Plus, and this 3 in red came from here. So 3 times mu s dt. So this is the process for this new derivative we made up. And that's a pretty uninteresting derivative. We basically just said take the stock and multiply it by 3, and that's our new derivative product. So what does this equation tell us? Well, it tells us stuff we probably just could have known without doing this operation, but what does it tell us? The expected value is the coefficient in front of the non-stochastic part, the 3 mu st. The standard deviation is the coefficient in front of the stochastic part. So the expected value is 3 times higher than the expected value of the original stock, which we kind of expected because we're just taking the stock and multiplying it by 3. The standard deviation, let me go back to that formula. The standard deviation, so when we crank out our new formula, after we compute the derivatives and second derivatives, we plug that into Ito's formula. We clean it up a little bit and we get a new Ito process. We get a new process that has a non-stochastic component and a stochastic component. The coefficient, this part will have an expected value of 0, right? Because it's a Wiener process times something. And the Wiener process has an expected value of 0, so if you multiply it by something, that'll also have an expected value of 0. The coefficient in front of here will be the expected value for the whole process, because this contributes nothing to the expected value. So the expected value ends up being 3 mu times st. And the original process was just mu times st. That was the expected value. That's how much it was expected to go up. Now it's going to be 3 times that. But intuitively, we probably should have known that. And then the standard deviation, how far off do we expect to be from this function that's multiplied 3 times the original function? We would expect the standard deviation to be 3 times higher than the standard deviation of the original stock. So, what do we say about the standard deviation? The standard deviation is 3 times the original standard deviation. This is the standard deviation of the stock, and this is the standard deviation of this new derivative, which is 3 times the stock. So when you square this component, the 3 ends up getting squared, and the sigma ends up getting squared, and ends up being 9 sigma squared is the variance. The variance would be 9 times the variance of the underlying stock in this particular case. And hopefully these results are intuitive. So, I mean, what I mean by hopefully this is intuitive, except for maybe the what I mean by hopefully they're intuitive, the 3 times the expected value should be intuitive, the standard deviation should be 3 times, and we should expect it to be 3 times more off the average. And then based on our definition of variance, we should know that that's ends up being 9 times more variance. Okay, so Ito's lemma applied to a forward process would be this. So here's another example. So recall that a forward contract is priced as follows. The forward contract, let's say we have a forward contract on a stock which is selling at a current price today, S0. And then we want to pick up a price in the future to say 2 people are going to exchange that stock for that price in the future. And this would be assuming there's no carrying cost, so there's no cost to hanging on to this thing, like a barrel of oil. So we'd end up just tacking on interest. We'd say the interest rate for the amount of time, that's what the price that they should agree to sell it at in the future. So just a little reminder, the stock price is currently, as an example, $100. The interest rate is 5%, the time is 1 year. The forward price right now should be 105, meaning they would sign a contract today to purchase this thing. One person would sell it and one person would buy it, and the price they would agree at would be 105 1 year from today. Okay, so this now ends up being our function, g. If this is an Ito process, and this function is a function of s and t, and again, we have an example where it's a function of s but not of t, then, oh no, I'm sorry. Yeah, so in this case, we are interested in the forward process, and let f and s be the forward price and the stock price of the underlying stock at a random time between now and t. So if that's the case, at any point in time in the future, the forward price should be, if you go so many months down the road, should be the stock price at the present moment times interest for the remaining amount of time left on the forward. So this would be the formula for the price from now till the time it expires. Okay, so now we go and we compute again the derivatives that we need for this. The derivatives we need for this computation, to apply to Ito's lemma. We need the first derivative with respect to s. We're going to also need the second derivative with respect to s, and then we need the derivative with respect to t. And in this case, it is a function of s and t. So the first derivative of the forward with respect to s ends up being, it was S times this thing. And this component is considered a constant with respect to S. So this ends up being the derivative of the forward price with respect to the underlying stock price. The second derivative of this is now all considered a constant with respect to S. So the second derivative would end up being 0. And the derivative of our f function with respect to time ended up being, S ended up being a constant, time ended up being the exponent, and e to a variable would be the derivative. It would end up being negative the exponent in front of the variable t. So this -1 would end up coming down as the exponent in front of the original function. So if you remember that the derivative of e to a number, where the function, the variable of integration is in the exponent, it ends up being whatever the derivative of the exponent is gets put down in front of as a coefficient. So that's kind of a calculus 2 thing, if that doesn't ring a bell. So this ends up being the derivative of the forward price with respect to time. So now we plug these derivatives into Ito's formula, and we get, so basically this is Ito's formula, like the textbook version of Ito's formula. All I really did was everywhere we saw a G, I made it an F, because we're doing the forward. And then we plug in this formula and we get, we end up getting this part, this is the non-stochastic part, and then this part over here is the stochastic part. So what does this tell us? Well, this component would end up, could give us the expected value. And this component would give us the standard deviation for the variance of the forward, not the underlying stock, but the variance of the forward, which could be different from the underlying stock. So substituting F for S e to the R capital T minus T. Now just this technique is going to be an example we'll do right after this, but the idea that we put F in, calculated the formula out with these terms in it, and now we substitute the F's back in, it makes the formula clean up a little bit better. So now we're saying that the process for the forward, using that stock as an underlying stock, ends up being mu minus R times the value of the forward. This is the non-stochastic component, and then sigma times F would be times dz or dw. This would be the stochastic component. Okay. Now, this R ended up being the interest rate. Mu ended up being, mu came from the expected growth of the stock, the underlying stock. So in a risk-neutral world, what would we expect a stock to grow at? In a risk-neutral world, it would grow at the interest rate. So in the risk-neutral world for the stock investors, the mu and the R, we might expect those to be equal to each other, which makes this component go to 0. So under that assumption, this component goes away, and the only thing left is the variable part. And what does that mean? Well, that means that the forward price is expected to be, the forward process is expected to stay at 0. It's not expected to change. The expectation is that the underlying stock will go from 100 on a smooth curve right up to 105, and if that's the case, this thing doesn't change at all. But this thing could change. It could go up and could go down, but the expected value would be no change over time. Okay, and then I think we have a little analysis of it. Okay, so the expected value for the forward would be the expected growth of the underlying stock minus the interest rate. If that comes out to be some non-zero number, there might be some examples we'll go over where these two do not match. if that's the case, then whatever this comes out to be times the value of the forward. That would end up being the expected value of the forward as time goes on. The standard deviation of the forward is exactly the same as the underlying stock in this case. That's not always true with Ito's lemma. You don't always get the same coefficient originally, but in this case you do. Okay, and then I'll go over another example. This is a pretty popular example. This is an example where we're going to take a stock, and I'm kind of doing this for a mathematical reason, then we end up getting an interesting result. So we want to come up with, this is again an application of Ito's lemma, we want to come up with a function, and what we'll do is, maybe it'll make sense as we crank it through why we chose this function. But we're going to use the function y of t is equal to the logarithm of the stock. Now notice that y of t is not a function of t, just a function of s. But that's allowed in Ito's lemma. It doesn't have to be a function of s and t, it just could be a function of s and t. So we calculate the derivatives, and the second derivative with respect to time ends up being 0. That's usually the middle one, so have these two swap. The derivative of log of s of t is 1 over s of t. So you might remember that from calculus 2. And then under Ito's formula we have 1/2 the second derivative. That would be the derivative of this part, the part in red. Its derivative would be negative, so this is s of t to the minus 1. That becomes negative 1 times s of t to the minus 2. And then that is also put in front of this. That's part of Ito's lemma. And then over here we have the first derivative of this function with respect to t times sigma s of t. Okay, and then we clean this up a little bit and we get, here's where it starts to get interesting. Here's why this is an interesting choice of a g function. This 1 over s of t perfectly cancels out this s of t. And this s of t squared in the denominator perfectly cancels out this s of t, which comes from Ito's formula. So the s's are all gone. I'm sorry, 1 over s of t here cancels out this one. So it's a perfect function in that this function, after you calculate the first order and second order derivatives, they perfectly cancel out the powers of s that Ito's formula gave us. So it was an interesting one, and eventually somebody would pick to use this as their g function because it cancels away all our s values. So now we have this new formula coming out of Ito's lemma, which has no s in it at all. The stock price is not there anymore because we happen to have chosen this. Okay, so now we have this new Ito process. So just to recap, the underlying stock is an Ito process. You can dream up any function you want for g. We let it be log of s of t, and then run it through Ito's formula to see what it turns into. And what it turned into was this formula. So this is saying the non-stochastic component of the y function ends up being this. This would be kind of like its interest rate, and sigma times the Wiener process. So that ends up being the formula for it. And then if we wanted to integrate both sides, we can do that. So if we integrate this side, we get y of t, and then we're integrating over time of this constant times the variable time, and then doing the same thing with the Wiener process. So this is just another way of writing this formula. Okay, and then going a little further, I'm just kind of rewriting what we had before. Y of t equals the log of s of t. And now what I'm doing is I'm saying that's the log of, and now I'm repeating s. So this is the original equation for s. So just one thing, like the original equation for s, what I mean by the original equation for s, let me go back to the very beginning. All it is this formula integrated. So this whole, Ito's whole lemma starts off by saying we're starting with this and then dreaming up a g function and then applying that function to getting a new formula. This is the original stock formula. If we integrated this, we would get S of t equals the stock price, the initial stock price as a starting constant, and then these two components integrated. So all I'm doing there is I'm taking this formula, I'm basically taking this formula, which is the value for s, and I'm integrating it. I'm sorry, it's the derivative of s, and then I'm integrating it to get a function for s. So when we get to the point where at this stage we're saying y of t, the function we originally dreamed up to be our g function for Ito's lemma, is equal to the log of the underlying s of t. So another way of writing the log of the stock price at any point in time t is to say it's the log of, and then this is that original formula just integrated. Okay. And it is also true that the stock price at any time is equal to e to y of t, right? Because log and e are inverse functions of each other, right? If this statement is true, then this statement is true, right? Log and e rate, this would be natural log actually. The natural log and then e to something is the inverse operation of each other. Just like multiply and divide are inverses and plus and minus are inverses, log and e raised to the are inverses of each other. So if this statement is true, then this statement is true. So now we could take this statement and say the stock price equals e to whatever y is. And y ends up being this thing. So now I'm substituting this formula down into here. So log of a constant, if I say e to the log of a constant, that becomes the constant itself. So this s, which is in the log, when I raised e to the constant, it became the constant itself. And then now I'm saying e raised to the, so this whole expression is the exponent. This ends up being integrating what's left. It's integrating this part and integrating this component. So these now constants are coming from the fact that we got rid of the s terms in the previous formula. So from y's point of view, we ended up with just these constants with all the s components gone. So taking this formula, this sigma, and then this coefficient in front of the non-stochastic component, the mu t minus sigma squared divided by 2, which came out of Ito's formula, we plug that into this last formula. And this ends up being another way of saying the stock price is equal to, this is a process for the stock price. So we arrived at this formula maybe by lucky guessing, or just somebody coming up with the idea that you take using your g function for Ito's lemma to be, well, we use y here, but this could have been g. So y equals log of the stock price. Run that through Ito's lemma. It perfectly canceled out every term to do with s. So we ended up with a formula that had nothing to do with s in here. And now we could say the stock, we're basically rewriting the stock process by saying whatever its current value is at time 0. If we want to know what do we expect it to be at a time t, it ends up being the stock price at time 0 times e raised to the, and then we just got a system of constants out of Ito's lemma. So this is another way of writing the process of the original stock. So let's see some interesting. This is a geometric Brownian motion with u and with mu and sigma as constants. Note that y of t, which is equal to the log of s of t, is normally distributed. So y ends up being the original function y, after we calculated it out, is the y function is normally distributed. So we have basically these constants, and then we end up with well, it's normally distributed with sigma as its variance, sigma as its standard deviation. So y is a normally distributed process, and the stock price is not actually normally distributed, but we're going to say it's a so-called a log normal distribution. So it is, if you took the logarithm of the stock price, it would then be normally distributed. So we say that the stock price itself is log normal distributed. Okay, so these are some examples, and again, some of these are coming out theoretical. If you wanted to apply this, probably in our textbook, they start giving you what the sigma and the mu's are, and then ask you for a concrete answer. So, but this is basically the formula that we're cranking through to get to those examples. So I think like our textbook, I think it has an example where, like this first one I did was where we just tripled the stock price. I think they have an example, I think one of the questions was not using 3, but using n. Yeah. So basically, if G was n times S, so many, multiplying the stock by any number n, what would it come out to be? And so if we know we went through the process, it would end up being whatever n is would show up here. And that's kind of intuitive. If the stock price was 6 times bigger than, if the derivative was 6 times the underlying stock, the expected value should grow by 6 times. The variance would then grow by, the standard deviation would grow by 6 times the standard deviation of the stock, which means the variance would grow by 6 squared, 36 times the variance of the underlying stock. So that was like the question in the textbook was a little more theoretical because we didn't use a concrete number like 3. It said it was n. And then just wanted you to go through this. And then, so it ended up being, the variance would be n squared times the variance of the underlying stock. And the expected value would be n times the expected value of the underlying stock. So if you thought of an example where the function g only was of t, not of s, it should still work. Yeah, I mean, Ito's lemma should still be true. So what would be an example like that? Suppose we said our function g was 2 times t. Would it matter? I mean, would Ito's lemma still apply? Let's say it was whatever t is, multiply that by 2. So the derivative with respect to s would be 0, the second derivative would be 0. This would be, let's say it was 2t, this part would be end up being 2. So the new process would be 2 times dt plus I was hoping the wiener part would cancel out. Oh, yeah, it does cancel out. Okay. Yeah, this derivative would be 0. So the wiener part would be gone. So then it would just be 2t. So if you said I mean, this is kind of a meaningless application of Ito's lemma, but if we said, here's our underlying stock, and then our g function is just g equals 2t, basically means we're not even interested in this thing. We're just saying whatever t is, multiply that by 2, and that's the price. So Ito's lemma would still apply. The wiener part goes away because we need the derivative of your g function, and if you don't include s, the wiener part will go away. The stochastic part would go away. and the only thing that would be left was the derivative of your t function, and then multiply by dt, which means it would just integrate back. So it's anytime you come up with a function that does not use s, any g function that is just of the variable t ends up pretty much being pointless. The Wiener part will go away, and then whatever the t is will just get differentiated and then get integrated back, and you're right back to your original function. So Ito's lemma only really becomes meaningful when your g function includes s. Using t is optional. We did an example with t tonight, we did an example without t, and in both cases the results had some meaning. We could start looking at what the expected values are, and we could start to see, will this new derivative product you're dreaming up, will it be more volatile, less volatile, or maybe the same amount of volatility as the underlying stock? So you're now in a position to start dreaming up new derivative products. You could say, I'm coming up with a product that takes half the value of Microsoft and a quarter of the value of IBM and multiplies the whole thing by 6, and that's my new product. And then you want to know, what's its volatility going to be, what's its expected value going to be, and you could use Ito's lemma to come up with that. So the biggest, most famous g function to apply to Ito's lemma is a function that will be a process, if given an underlying stock, what would the value of its corresponding call option be? So if we were to plug in a call option formula, so first of all we'd have to come up with a formula, g, for a call option. Given s, how could we come up with a formula that describes the call option for that stock? Then once we know that formula, g, we would run that through Ito's lemma, take the derivatives, clean up the formula, and then we would be able to say, okay, this is the expected value it's going to be, and this is the variance it's going to be. And from the expected value, we could calculate what its current price should be. So anything we do, we could always get its current price out of the coefficient in front of the first part, and we get an idea of how random it will be by the coefficient in front of the second part. So the Black-Scholes equation is basically doing just that. They did step one, they said we're not going to come up with a formula for the call, we're going to come up with a way of replicating a call by taking a series of buying and selling and borrowing money to have a process that is exactly like a call. We'll come up with a formula, a G formula for that, run that formula through Ito's lemma, and come out with a process for the call simulator, and then say to ourselves, this part will tell us the expected value of it, which means we could use the expected value to figure out what the price should be today by figuring out what the expected value will be in the future. And then the variability part, to a risk-neutral minded person, won't matter. So that's probably the most famous use of Ito's lemma, is Black-Scholes equation for pricing an option, pricing a call option.